you very much, and hello everyone. So really good to be here. So I'm Adam Tornhill, and I'm going to tell you a little bit about me in just a minute. Before I do that, my goal today is to share my experience of building large-scale systems with Clojure, and we'll meet both the strong parts as well as the possible pitfalls. But before I jump into that task, I have to do what I always tend to do. I have to start with a bug fix. Because it occurred to me that it's actually not 5 years with Clojure in production, it's 7. Because we deployed the first version of this product I'm going to talk about, the experience of building it, called CodeScene, back in 2016. So 7 years in production, 2 additional years of experience. Anyway, enough about that, a little bit about my programming background. So I started to code at a very early age. No, really, I didn't. This isn't me. This is actually my son, who a couple of years ago got hold of my practical Common Lisp book. And what you can see in this photo is that just seconds after I took this photo, my son started to kind of tear out a couple of pages of that book. And I was pretty convinced that, that's something he wanted to keep as a reference. So I'm a very proud dad. My journey into Clojure was fairly traditional, I would like to think, for someone of my generation, because I started to code in the late 1980s on this wonderful machine called C64. And I think some of you kind of share that experience. It was actually a pretty fascinating machine, because one of the big benefits of a C64 was that you couldn't even load a game without actually typing in basic commands. So it was like encouraging to kind of start to explore programming. So my first programming language was actually BASIC. And that puts me into that category that Dijkstra, a couple of decades ago, he wrote that it's practically impossible to teach good programming to students that have had prior exposure to BASIC. As potential programmers, they are mentally mutilated beyond hope of regeneration. So that's where I'm coming from. But that didn't stop me, because after that, I went into assembly, C, and Pascal, some of these big languages 30 years ago. And around the millennium, I started to work on various object-oriented languages, spent a lot of time with both Java and C++. And around 2005, I took a slightly different career path, because I'm an engineer by training. But one of the things I wanted to do was to kind of explore the human element in programming. Wanted to understand a little bit how we developers, how we think, reason, and solve problems, but also how we collaborate with others. So I actually took and spent 6 years at the university studying psychology. So that's still one of my big interests. And somewhere around that time, I also read this wonderful essay, still one of my favorites, called Beating the Averages by Paul Graham. And that had a massive impact on me, because what Paul basically shares in that essay is how using Lisp kind of helped them outcode their competition. So that was a big inspiration for me, and that's where I first started to look into this Lisp family language. And I spent a couple of years playing around with mostly Common Lisp myself, did a little bit of Scheme, but mostly Common Lisp, and I actually ended up writing a book about it called Lisp for the Web. So it's a book I published like 13 years ago now. It's still available on LeanPub. So if you want to have a look at it, please go to LeanPub. It's completely free as in beer. And after doing that, I had some initial experience with functional programming after embracing Lisp. And I had the chance to work on a large-scale system written in Erlang, which was really fascinating. I'm going to talk about that in just a minute. And after working with Erlang, I also picked up Clojure, and I used Clojure to kind of build tooling as a proof of concept for the techniques I wanted to show in my previous book called Your Code as a Crime Scene. So Your Code as a Crime Scene is very much about a set of techniques that you can use to get insights into large-scale software projects. So I used Clojure to kind of build those tools. It's still open source on my GitHub. But anyway, I like to think, and yeah, after writing that book, I kind of realized that these techniques, if I want them to become mainstream, there has to be some really good tooling around it. So that was like my main motivation to kind of found CodeScene, which I did in 2015. So the company has existed for 8 years now. and we had our first version of the CodeScene tool in production in 2016. But if we look at this timeline, we kind of see a path here. It's somehow a path towards higher and higher abstractions and further away from the traditional machine architecture that I was very close to when I programmed in assembly or C. And what I always found interesting is this productivity debate, right? Because is it really true? You know, like Paul Graham once claimed that we are more efficient in a higher level language, like let's say Clojure. And the interesting thing is that I actually have some data on this. I actually have some data on if functional programming really delivers on its productivity promise. And there's a backstory to this. This all happened in early 2010, because at that time I worked as a software architect on a project. We were going to do a prototype for a simulation platform. And this simulation platform had a couple of properties that were interesting. First of all, it was supposed to be a soft real-time system. It also had to scale. It had to scale across multiple servers, and it had to scale to lots of potential users with a very dynamic load. And it, of course, had to be super responsive. And it was supposed to be written in Java. So we kind of wrote the initial prototype and proof of concept in Java, which I knew pretty well at that time. But when I kind of understood those requirements, I kind of thought that this sounds very much like a perfect fit for this strange language I've been hearing about at a recent conference called Erlang. So I somehow convinced my management to sponsor a prototype in Erlang so we could kind of compare the two solutions, a Java-based and an Erlang-based. So we did that. And what's so interesting is that none of us that worked on that Erlang prototype actually knew the language. We picked it up as we went along. And what's so interesting is that I collected a bunch of data around it. And one of the first data points was that I looked at the size of the code base. So what you see here is that the Erlang code base was like 25% the size of the Java code base. So like the Java code base was 4 times as big. Despite the Erlang code base being so much smaller, it was much more feature complete. And it had much better performance, and it had better diagnostics and monitoring abilities than the Java solution, despite Java being so much more bloated. And when I presented this to my management to kind of evaluate these two solutions, I, of course, made a case for Erlang because, look, we can be so much more productive. Here's the proof. These are actual numbers. And, of course, you can guess which direction management chose to go. Obviously, they went with the Java version. And I mean, yeah, we can talk about that later, what arguments were for and against that. But at the end of the day, it kind of left me a little bit disappointed. Because once you have kind of seen the light of functional programming, it's very hard to go back and, you know, start to work on something where you feel like you're wasting your time. So the reason I think this is so important with the power of functional programming is when I start to look a little bit closer at what we developers actually do. Because for a long time, I thought that my job as a developer was to write code. After all, that sounds sensible, doesn't it? But it turns out that when you look at the actual research, that's actually not what we developers do. So I want to recommend this wonderful book to you. It's a book called Facts and Fallacies of Software Engineering by Robert Glass. And in that book, he has something he calls the 60-60 rule, where he basically says that 60% of our time is spent making modifications to existing code, right? So that's already the majority. And another 60% of that time is spent trying to understand what the code does in the first place. So to me, the takeaway is that no, as developers, we don't really write code. What we do is we're in the business of trying to understand code. And to me, that means if we want to optimize any aspect of software development, we should optimize for ease of understanding. That's where the big win is. And that's where I see functional programming and Clojure in particular being a really good fit. So let's talk a little bit about Clojure and functional programming. Because as you probably know, functional programming is not a single thing. It's more like a continuum of things and different languages that kind of emphasize different aspects. So there's this really good quote that I like by Fogus and Hauser, where they claim that, you know, you ask 100 programmers for the definitions and you likely receive, I would like to add, at least 100 different answers. But personally, if I kind of take a step back and think about, given my experience with Clojure, what have I found most useful in the real world? And there is a clear winner. The one thing I like the most with FP is immutable state. Because immutable state, it's a pretty simple idea with implications that go deep. Because what we do with immutable state is simply that we remove all mutable operations. We basically take out the assignment operator. There is no such thing. And when I mean take out the assignment operator, I really mean getting rid of it, right? Once we have bound a particular symbol to a value, that will never ever change. And that guarantee is really fundamental to me because it's really the foundation for all of the power I see with Clojure. And I would like you to kind of, maybe you're already big fans of immutable state like I am. That's probably one reason you're here, but I still really want to drive home my point and have you experience the benefit of immutability. So the way we're going to do this is by having you do an IQ test. I know, you definitely weren't prepared for this, but guess what? This is what happens when you put a psychologist on stage. So let's do this together and feel free to post your answers in the chat. So here's the first test. If you've ever done something like this before, you recognize the pattern. So at the top, you have a series of different patterns. The last one is missing, and your task is to find the missing pattern from the bottom two rows, right? So the right answer here is one of those numbers, 1 to 8. Which one completes the pattern? So who wants to drop something in the chat here? Oh, we already have one answer. We have lots of answers. Wonderful, wonderful. Thank you. You're doing great at this because, of course, it's 8. That was super simple. So I think we need, after all, this is a Clojure meetup, right? So I think we need to raise the bar a little bit. So let's try this one. What's the missing piece? Let's see, are there any answers coming in the chat? Not so many. Interesting. Oh, there's one. Yep. So we have 2 people, 3 people, lots of giving the right answer. And the right answer is, of course, this one. Well done, very well done. And if you thought that this one was hard, then it's actually supposed to be really hard. So you can always look at the link in the bottom right corner, because you see this is an example that I ripped from High IQ Pro, right? So it's supposed to be super hard. Now, what I found so interesting is that if we start to think about why it's hard, because if we go back and think about the previous test we just did, where we had lots of answers within a very short time, the way you do it is basically that, yeah, you have to remember the first pattern, then you have to remember the second pattern, and then you have to kind of mentally put them together. It's like an addition. And then you get the answer, right? So as soon as you recognize that pattern, you can solve it. And to recognize that pattern, you need to keep 3 things in your head. The two pictures, and then the result you get from mentally merging these. If you look at this one, it's significantly harder, because here as well, you need to keep the 2 images. If you go row by row or column, it doesn't matter. You need to keep 2 images in your head. Then you need to kind of intersect them, and you need to remember not only which images, which lines in those images that overlap, but also the ones that don't. So it's like a combination. It's like an XOR, right? So an addition and a subtraction. So here you need to keep many more things in your head. And this is interesting because keeping a lot of things in your head kind of touches upon one of the cognitive bottlenecks we have, our working memory. There are only so many things we can keep in our head and reason about effectively. And an IQ test kind of stretches your cognitive working memory to its maximum. Coincidentally, an imperative programming style does exactly the same thing. So let's look at a program here, a small snippet of code. And we see that this code is not only is it full with side effects, there's also a lot of state in here, right? So each time I kind of call something mutating, or I mutate some variable directly, I introduce a state change. So it's a simple function, but we also see that this style doesn't scale really well cognitively, because all of this complexity quickly adds up, and it kind of taxes our working memory. It becomes virtually impossible to reason about the mental state about what's actually happening in that code. So my number one recommendation to you today is to avoid this. Don't turn your code into an IQ test. And more specifically, functional programming and Clojure helps a lot with that, because immutability is what allows us and allows our programs to scale in cognitive terms. And to me, this is the absolutely biggest win. So I hope that makes sense to you. If not, then we will have an interesting discussion afterwards. So what I want to talk a little bit about now is that once I started to work with Clojure, there were things, some of my habits that I had to kind of reconsider. And one of those habits was test-driven development. And for the context, I'm a big fan of test-driven development. I've been using it for a long, long time. 15 years ago, I taught courses in TDD, so I'm a big fan of it, and I find it incredibly useful. The only problem I have with TDD is its name, because the name test-driven puts way too much focus on test, because it's not really a test methodology. TDD to me is a design method. And the reason that TDD works so well is because it allows us to take a large problem and break it down into much smaller and more manageable chunks that we can fit into our head, right? And we can design these pieces interactively, right? So TDD more or less, emulates the effect we get from a REPL in our imperative language. That's one of the big wins with TDD for me. So when I started to work on Clojure, I of course started TDD style, but I kind of found that since Clojure is so high level and so incredibly interactive, I found that TDD kind of got in the way a little bit, because it made it harder to kind of switch and explore various directions. So pretty soon I found myself embracing a different style. So what I do is I spend most of my time in the REPL. So I kind of quickly prototype, iterate, and learn about the problem I'm trying to solve. And once I kind of have a good fit, what I do then is I take my REPL session, I literally copy paste it into a unit test suite. And then I kind of turn the REPL session into unit tests. And then I go through it and make sure I cover edge cases and stuff like that. So this is a style that has worked pretty well for me over the years. However, on one observation I did after doing this for a couple of years, then it kind of occurred to me that my unit tests, the ones that I get out of a REPL session, they tend to look very, very different compared to the unit test I write in, let's say, Java or C#. In particular, what I noticed was something that had to do with the test setup. So let me try to explain this. Because if any one of you have been working in an object-oriented language, know that having a test setup method is something you need for virtually all unit tests. And I want to show you what these can look like. So what I'm going to show you now is the test setup method from a real-world code base. This is ASP.NET MVC from Microsoft, a framework for building dynamic web applications for the web. And what's interesting here is that we see that this is a pretty long test method, but it's really just the start of it. Here's the rest of it. So now imagine what this actually means. What this test method does is to create a lot of state. And now every single one of our unit tests executes within the context of this state. And that means that when something goes wrong, not only do I need to understand my unit test, I also need to understand all this state that I somehow need to fit into my head. So it's no wonder that working with code like this is quite painful. And that kind of led me to form one observation that, to me, the length of a test setup method is inversely related to the readability of the code under test. So long setup methods are always a symptom to me, a symptom of overly complicated code with too much state. But what I observed in Clojure was that since we have immutable state, when I counted setup methods across CodeScene's codebase and all the unit tests, what I found was that there were exactly 0 of them. There was not a single setup method in the unit test. Why? Because you just don't need them, right? Without immutable state, you can kind of have the complete state in every single test. And note that this comes from a code base that has more than 90% test coverage and is almost 8 years old by now. So immutability definitely delivers upon its promises when it comes to testability too, in my experience. Now, another thing I really, really like with how Clojure kind of fits with the cognitive view of programming is threading macros. Because what I have found is that virtually all code becomes so much simpler when we start to focus on collection of things instead of having to deal with special cases. Because by using this pipeline style, what we can do is that not only can we express the algorithm in very natural steps, right? It's something you can read top to bottom and actually understand what's happening. It's also very easy to modify. So I find that this works really, really well with rapid prototyping, right? You throw something together and then you realize, okay, yeah, I need to get rid of this particular type of value. I need to change this, right? You can add these separate steps into the pipeline and it will just work as long as you kind of stick to the contract between the different stages. What I also like is that there's a minimum of conditional logic with the pipeline style, right? So a lot of the stuff that would be if statements or other conditionals in an object-oriented imperative languages is now replaced by things like filter or remove. And loops, of course, we don't really do explicit loop, right? We have higher level functions like map and reduce. So I'm a big fan of the pipeline style. It simplifies code a lot. What's also interesting, and when I started to work in Clojure, was that when I looked at code like this, it looked incredibly inefficient, right? It looks super inefficient on imperative mind, right? It looks like you're looping over the same stuff over and over again. But of course, that's not really what's happening thanks to lazy evaluation, right? So we're really, really only making one pass over this particular input sequence. So to me, the result of this pipeline style of coding is the best of two worlds. Not only do we have the simplest possible code, it's also very, very often performant enough. However, I like to point out that lazy evaluation isn't really a free lunch either, but we get to that in a couple of slides. Before we do that, I want to talk a little bit more about the problem area we work in, the domain and its architecture. Because now I have talked about a bunch of smaller stuff like unit testing and pipelines and so on. But what I want to talk about now is systems. Why? Because there's a gap between what we tend to see at introductory conference talks or introductory tutorials, that most examples, they look like this, what you see on screen here. But then what we are supposed to build looks very much more like this. And maybe it's better now, but when I started 10 years ago with this stuff, I found it really, really hard to see how these smaller pieces would fit together to form a system, a functional architecture, right? Something that has to deal with non-functional side effects and the rapid feature growth of an evolving product. So how do we do that? I'm going to come back to that. Before I do that, I want to show you what type of problem we are solving, because I'm going to use that to explain the architecture as well. So CodeScene is a tool that works in the domain of behavioral code analysis. And the idea of behavioral code analysis is that the code itself, the way it looks, is important, right? We need to know if something is good or bad. But it's even more important to understand how the people behind it, the people organization, interact with the code they're building. That's where the big value is. So CodeScene is a tool that you can use to get under some situation awareness of a code base, prioritize technical depth and stuff like that. And I really don't want to turn this into a CodeScene presentation, so I just want to show you some quick examples so you know what you look at later. So the first example I want to show you is how we can make sense of a code base and try to find bottlenecks and technical debt. So the example I've shown you here is MongoDB. Some of you might know Mongo. It's on a document database, was super popular a couple of years ago, still in heavy use. It's a pretty big code base, 1.3 million lines of code, developed by more than 700 people. So this is a large-scale code base. And what you see on screen here is a visualization inside CodeScene of MongoDB. So the way you read this visualization is that if you look at that circle in the middle, the one that looks like a bacteria culture gone mad, and the way you read this is that it's actually a hierarchical visualization where each folder in the code base is visualized as a circle, the ones I'm hovering over right now. As you see, it's also an interactive visualization, so it always follows the structure of your Git repo, right? So if this was your code base, then we recognize the names of these circles as important components or, subsystems. And then when you get to the lowest level of detail, you see that each file with source code is visualized as a circle too. And you see that these circles, they have different sizes. Most of them are green, some are yellow, and some are red. So this color is used to reflect something I call code health. And code health is a metric, and everything I'm showing you now is something we implemented using Clojure. So code health is a code level metric. And for the context of this presentation, the way it works is that we take a piece of code, the one we want to analyze, we parse it, right? Build up an internal abstract syntax tree. And then we analyze that syntax tree for a number of code smells. So to give you some examples, at the module level, you might want to look for things like low cohesion, a module having too many responsibilities, lack of modularity in general, right? Squeezing too much stuff into the same class. At the function level, you want to look for design smells like brain methods. That's something you might know as gut functions. And gut functions, they are simply these overly large functions. They're always really, really large. They contain a lot of logic, and they are very central to the class in the sense that each time you want to modify something in that domain, you end up in the gut function. And over time, it just becomes more and more complicated, right? So maintenance nightmare. Could also be classic, like copy-pasted code, primitive obsession in statically typed languages. And at the lowest level of detail, you want to look for different complexity patterns. And to give just one example, you want to look for things like deep nested logic, right? That's when you have if statements inside if statements inside if statements, and then a loop for good measure, right? Because those patterns are known to be responsible for like 20% of all programming mistakes. So anyway, by kind of identifying all these code smells, what we can do next is we can take those code smells, we can kind of score them. They have different weights, they are important in different ways, but we can also aggregate and categorize every single piece of code as being either green, which means healthy, easy to understand, yellow, problematic, we have some tech debt there, or if we're not careful, red, which means that this code is really, really expensive and hard to understand and maintain. So that's what we do. So that's what you saw in the previous picture was a code health evaluation of Mongo. So now we know where the strong and weak parts are of the code base. And what I also wanted to point out is that this code health metric, it actually correlates with the important business aspects like speed to market and the number of defects. So when we look at the picture like this, it's not only a vanity metric, right? It actually means something because we can see here that if I have red code, it can take an order of magnitude longer to implement a feature compared to green code. So that's good. So now we know that this piece of red code is probably an issue. But I have to reveal something to you. After working with code analysis for a decade, I have to say that finding unhealthy code is the easy problem. And the reason I say that is because there's so much of it out there, right? So deciding where to start is the much harder problem. Because if we look here at Mongo, if I zoom out a little bit, we see that there's a lot of red and yellow code. So where do we start? One thing we can do in CodeScene is we can use this feature here. We click something called refactoring targets. What happened now was that the tool somehow magically knew that, okay, given all your red code, the one you should focus on first is this particular file. The way we figure that out is not by looking at the code. What we do now is that we look at our Git repository. So we take the Git data, we mine it, we parse it, and we look for various patterns. One of those patterns is that we look at how much development activity is there in every single file. Because you can have highly complex code that's stable and just works in production that you never touch. That's not really the problem. The problem is that complicated code that you have to work with every single day. that's where the risk for defects and waste is. So that's how we can figure out that, okay, this seems to be technical debt with high interest. But it doesn't always stop there. Because in this case of Mongo, let's look a little bit closer at this. If I look at this particular hotspot in Mongo, what I see now is that this particular module is quite large. It's a file with almost 5,000 lines of code. And refactoring 5,000 lines of code, it's going to be a nightmare. So we need to prioritize a little bit deeper. And the way we do that is by taking that file, parse it into separate functions, then we look at the Git log and see where do each commit hit over time, and sum it up so that we can get these hotspots and refactoring targets at the function level. So in this case of Mongo, I would say that the top two functions, finish load local config and start load local config, we can kind of hear from the names that they're related. So maybe that's like a small responsibility waiting to get out and to be refactored. So this is the techniques I use to kind of an actionable starting point for refactorings. So that was one use case. I want to show you a last one too, or a quick one, because I want to show an example on how you can go beyond code and get insights into other aspects of software. And one of those aspects is something I call knowledge distribution. Basically, how familiar are we with a team, as a team, with a code base? And for this case study, I want to look at the actual Clojure code base. Because Clojure is a super interesting code base to analyze. First of all, it's really, really small. It's 76K of code. Of course, 76K of code is a lot for a single developer, right? But it's very, very small compared to systems like MongoDB. We also see that there have been 181 developers working this piece of code. And 181 contributors. The interesting thing about that is that that number doesn't really reveal the whole story. Because as we see here in the box to the bottom left, the one called key person dependencies, we see that actually a large portion of the Clojure code base is written by a much, much smaller core team. So one business question we could ask ourselves is, okay, but what happens if one of those core contributors leave, if they never ever want to contribute to the code base again? What's the impact of that? For example, what would happen if Rich Hickey decides that he never ever wants to touch Clojure again? Well, let's have a look. So let's look at another visualization. So this is Clojure visualized. It's the same visualization style as we used for MongoDB. So we still have the packages here. We look inside them, and then we see the various files with implementation. So that's the actual language and runtime. And we also see that the colors carry a different meaning, because the blue color indicates that the majority of the code is written by the current contributors, right? So that's people that are actively contributing to the project. So in this case, we would have perfect knowledge of the Clojure code base as a collective. That's really good. What we can do now is we can simulate the impact if Rich decides to leave. Where will the knowledge gaps potentially be? So what I do now is that I look in the list to the right here. We have a list of all contributors, and I select Rich Hickey and I tick the box, and boom. Everything indicated in red, that's the part of Clojure where Rich is still the main contributor. So here's something called Clojure core. Maybe that's important. If we look over here, we see that, oh, we're going to lose the majority of the knowledge of the compiler. So I never contributed to this code base, so I don't know that much about it. But to me, even to me, a compiler sounds like it's kind of important. So if this was our code base, right, then it's probably something we'd like to know about. And maybe we would like to inspect this particular compiler and say, okay, is that code really, really simple to understand? Because if this person will really leave, then we will have to make sure that we understand it to continue to maintain it. So that's an example of our social analysis. So now that you know a little bit about the domain I'm working in, I can talk about some of the specific challenges we had with using Clojure. So one thing that happens every now and then is that we have to analyze these massive code bases. So we talked about MongoDB on 1.3 million lines of code. That's tiny compared to something like a Linux kernel. So what you see on screen here is 21 million lines of code written by more than 15,000 developers. And the thing is that when you analyze a code base like this, the first thing you notice is that it takes forever. It takes a long, long time, because at some point you have to kind of take every single file with source code and you have to parse it and you have to analyze it. And if like CodeScene, you're a behavioral code analysis tool, it often means that you need to analyze its history as well. So the same file, you probably want to analyze like hundreds of revisions, right? And you don't want that analysis to take a day. So you look for ways to speed it up. And one of the things I found pretty early on, because this was a bottleneck in our analysis, what I found was that Clojure and functional programming in general makes it embarrassingly easy to parallelize work. So what I did was basically something like this. We had some code like this, where we had this function that could calculate the code health of a bunch of files, right? So we have the files in the code base, we apply this function, and we kind of get the code health of each one of them. What I found was that by just adding a single character, I could speed this up by a factor of 10. So here's the magic character. I went from a map to a PMAP. And now suddenly the whole analysis was 10 times as fast, because I could parallelize so much on all the different cores. So this was wonderful, right? And it actually worked fairly well. However, at this point, I do have to make a quick fix to my slide, because concurrency made easy should really, really spell concurrency made possible. Because one thing I learned is that concurrency is never easy. Because there are always things like you want to control the number of cores you fan out to, right? So you don't kind of just clog the machine. And you also have to be careful about the memory allocated to each thread and stuff like that. So in practice, it turned out to be a little bit more complicated. And what we ended up doing was to actually use a library, to use the clay pool, so that we could kind of control the thread pool size and stuff like that, and reuse the thread pool when applicable. But I still have to say that pure functional programming makes it embarrassingly easy to parallelize code. And this turned out to be a big, big win for Clojure. Now, let's raise the abstraction level a little bit and talk about the architecture. So the first thing I learned was that at the macro level, building a software system using a functional programming, it's really not any different, right? It's the same boxes and the same arrows, right? And also when it comes to deployment, right? Functional programming doesn't really offer any benefits there. It's the same deployment tools we have to use as for any other solution. So at the highest level, it looks like any architecture. However, what I found was that the subsystem levels, there is much, much more freedom and many, many more benefits to functional programming, as long as we follow one simple rule. And this is a rule that the times that I violated it, it has always came back and tripped me up. So that rule is to isolate side effects. So whatever we do, let's make sure that we really take the side effects and push them to the boundaries, to the edges of the system. Because if we fail to do that, then we lose many of the potential wins with functional programming, things like interactivity, testability, and ease of reasoning. So this is really, really important. And it's a tricky part, particularly with side effects. So what I found is that there is a pattern that worked really, really well in our context. Because now that you have seen this quick demo of some of the things that we can do with CodeScene, you see that what it's basically about is to collect some data from various input sources, maybe Git, Jira, or the code itself. And then we somehow transform that code maybe into an abstract syntax tree, and then we analyze it for various properties, right? And try to detect patterns in that. So one pattern that I found that models that really well is an architectural pattern known as pipes and filters. So you have a bunch of different pipes and different filters that you can simply combine in runtime. So one example on how this can look, so I have these different boxes with things I can pick and put together in runtime because they all kind of share the same interface, is that I could put together something like this. So a pipeline like this is something I could use to fetch some data from Git. I can filter in a specific time span. Maybe I want to look at the last week of development. And then I want to detect the development hotspots, and I want to give early warnings to our users that, hey, you have a hotspot that's moving in the wrong direction. So I would put that together using the pipes and filter pattern. And the interesting thing here is that the runtime behavior goes in this direction, right? It's regular function calls. But the results are then delivered purely functional without any side effects to this edge of the system where I might want to write this to a database or to a file or even present it to the UI. And what I really like about using filters in functional programming is that it's really turtles all the way down. Because remember the pipeline style that I talked about earlier? An architectural pattern like pipes and filters is very much exactly the same principle but applied at an architectural level. So now each function call represents an entry point to like a whole subsystem. And this is possible thanks to immutability and lazy evaluation, which makes it work in practice. So with that said, functional programming in Clojure really simplifies large-scale code bases. I'm super happy that I choose Clojure. But does that mean that Clojure is finally this long-sought silver bullet? Well, let's look at a couple of experiences I collected. First of all, I already mentioned that lazy evaluation is absolutely great. And that's true, except for when it's not. Because with laziness, it can actually be quite hard to reason about the code from a performance perspective. And we might have bottlenecks show up, much further down the pipe than where they actually are, thanks to the laziness. So this makes it really, really painful to profile code. And the way I tend to address this problem is that I tend to run different parts of the code step by step in the REPL and try to kind of, force the results and measure those partial results. So interactivity saves the day, but it's still painful with lazy evaluation in certain situations. Another very Clojure-specific thing is something I call the semantic gap. Because if I write some code like this to the left and I make a slight mistake, what I end up seeing is the stuff to the right. And we as a community, as a Clojure community, we are of course well aware of this gap. But I think the fundamental issue is that Clojure is simply very, very high level compared to the underlying computational model, because functional programming is very far removed from the underlying von Neumann machine. And this kind of abstraction, it starts to become extremely leaky the moment something goes wrong, right? Because now suddenly the stack traces, there's absolutely no relationship to what I see there and what I did with the code. So that's something that took me a while to get used to. Then another thing that was interesting, because it's something I expected to be much more of a problem. So when I started to work on Clojure, I was a little bit worried about the performance aspect because I know that we had to analyze a lot of code. And I was kind of hoping that I could use Java as like the assembly language of the JVM, right? So the way we did back in the day of C programming, we could always branch out and do something in assembly if we needed to hand optimize it. My thought was that I could use Java for the same purpose in Clojure. And it actually works quite well. However, what surprised me is that during these 8 years that I worked on CodeScene, I had to do this once, exactly one time. There was a single algorithm that I just couldn't make quick enough in Clojure. That might be due to my limitations as a Clojure programmer, but I actually ended up writing that small snippet in Java. So I had like 50 lines of Java code. And I kind of told myself that, sometimes a little bit of mutability is exactly what the performance doctor ordered. So that really worked. But what surprised me is that Clojure was actually performant enough for like 99% of all the things we do. And again, I think it comes down to choosing the right algorithms and being able to program at the high abstraction level that Clojure enables makes wonders for finding the right algorithms. So I think that explains a lot of performance. So to wrap it up and move back to the beginning and try to answer this question, because by now I think you all kind of realized that I'm super happy with the choice of using Clojure. But what was my original motivation for choosing that language? Well, I had a couple of key questions that I asked myself very, very early on. And the first one was that when I started CodeScene, I kind of realized that a startup, it's not going to be an 8-to-5 job. Right, it's going to be something that I'm going to live with for a long, long time. And I knew that this is a choice that I make. But it also meant that if I'm going to spend my days looking at code, I want to make sure that that code is, one, beautiful, and two, that it's fun to work with. because I do think that fun is a much underestimated driver in software development. In fact, fun is very much a guarantee that things are going to get done. So fun was actually one of the reasons I chose Clojure, and it did turn out to be really fun to code in. The second thing I looked at was competition, because with CodeScene, we kind of entered a field where there were a lot of established code analysis tools, big players, and it was very clear that we, being a small team, we cannot really compete with those companies, using the same technologies. We have to do something differently to be able to compete with them. So this was one of the bets that using Clojure, we will actually be so much more productive and be able to iterate so much quicker that we can keep this team small and benefit from being a small team. And this is something that Clojure definitely delivered on. So that's a really fascinating thing to observe. Then the third thing is the community itself. And the Clojure community it's brilliant. I mean, there's so much amazing work being done in the community, the things you do, but also all the open source contributors, right? So there's so much mature Clojure code out there that you can stand on the shoulders of these giants. And we do try to contribute to open source ourselves. And the fourth thing I looked for in technology was that, when you bet your company on a specific programming language, you want to make sure that that's a stable language, right? Because I remember, right, back when I was a C++ developer, when I started to learn C++ in the 1990s, then 10 years later, the language looked completely different. And if I look at C++ now, 10 years after I wrote my last line of code in it, I have a really hard time understanding modern C++ because it kind of changes so much. And there's new stuff being added to it all the time. And this is a remarkable contrast to Clojure, which has been extremely stable. So if I just look at the contribution history in Clojure, I see that it's still actively maintained, but the core language hasn't really changed at all since I started to use it. And to me, this is a benefit, right? It's a feature, because it means that I can kind of continue to build on my experience and learn new things. And should there be any particular feature that I lack in Clojure, since we have macros, I can always add that feature myself. So that's another thing I love with Clojure being a Lisp, that I, as a developer, have the same power as the language designer. So with that covered, I just wanted to give you a couple of links if you want to read up more on this. If you want to read up about the code red studies and its linked to business impact, you find it here. The tools I use to do the analysis is of CodeScene, of course. So if you enjoy this, please have a look at it. There's a free community edition. It's always going to be free for open source. And if you want to understand more about the domain, then I actually have a second edition of Your Code is Crime Scene being released tomorrow. So to do a little bit of self-promotion, if you want to look at behavioral code analysis, you can probably do worse than read Your Code is Crime Scene. So with that said, I want to take this opportunity to say thanks to you all for listening to me. And I'm very much looking forward to discuss this. Thank you very much.